Write your own image loader. How hard could that be? We go to seek to the appropriate position and read the right number of bytes and save them into variables in a structure. Everything's got to be the right size. We'll be reading and writing in binary mode. That makes sense. These aren't text files. Decide on a way of representing an image in memory that has nothing whatsoever to do with bitmap format. I use a dynamically allocated array of unsigned long integer pointers, each of which points to the first element in a dynamically allocated array of unsigned long integers. Well, bully for you. Now write a bitmap loader. Now write a bitmap saver. Alright, Wikipedia. In typical uncompressed bitmaps, image pixels are generally stored with a variable number of bits per pixel which identify its color. But down below, 24 bits is what we want, but the bits representing the bitmap pixels may be packed or unpacked, spaced out to byte or word boundaries. That is a little concerning right there. That might be a problem. Alright, so we're going to have a header and pixel data, and I guess the pixels are kind of like little golf balls, and they got so much red, green, and blue in them. They're ordered blue, green, red in these old bitmaps. And that's the intensity of the color is a number. So 83 means more red. No one gives a damn if they're odd or even numbers. You'd have to have a twisted mind to even be going there. So our color range can be from 0 to 255, blue, green, and red. As long as you're not below 0 or above 255, everything should be cool. And because the odd or even pixels mean nothing to anyone else, I don't see any reason why we can't jack a ride on it and encode them with... So we should be able to encode characters using odd, even bit configuration. 8 pixels should give us 1 character if we can code this properly. Wouldn't be hard to change it by 1 pixel, you'll never notice. But this obviously isn't a pixel created by a deviant mind. How does the computer know odd from even numbers? Well, we're just going to tell it to divide everything by 2 and check the remainder. If it's a 0, it must have been an even number. If the remainder is anything other than a 0, it must have been an odd number. We're going to be dealing with characters in character format, in decimal format, and in binary format. We'll probably have to build arrays, and we'll do some fancy bitwise shifting of these here binary numbers that represent characters to be able to check for even, odd as 1s and 0s, and then encode them into the pixels. It's not exactly red-eye reduction, but... Okay, so there's 1024 by 768 isn't even a big picture anymore. That's 780,000 pixels. At 8 pixels per character, I should be able to put 98,000 characters inside that picture. You wouldn't even know it's there. So I got to read in a Windows bitmap image file, change all the pixels to even numbers, and save out a bitmap image that you can actually view. And if we can do that, I can create a handshake with 8 even pixels, 8 odd pixels, and it takes 24 numbers in sequence to make this handshake work. 48 bytes. Alright, create a bit flipper function that tells the encoder function if the pixels should be even or odd. Read in text characters, store them as binary numbers to be manipulated in a bitwise manner, weld that code together, and code text into an image, view it with a hex editor to see if it really worked, write a decode function, decode and display the text from a bitmap image file. Yeah, that's my homework. Okay, by the time I get to the 5th version of this, I can read in a bitmap image, and I can encode a handshake, and I've got hard-coded the letter A, and I can print that out in a binary format so I know I have access to that binary format. So 0, 1, a bunch of zeros and a 1, 65, that's an A, big A. 4 files. That's my binary. That's the source code to create binary. This is an ordinary everyday image of a blueberry plant, and this is a Unix or a text file about the subject Unix. And there's a textual representation of those 4 files. Now what we're going to do is use my new program that took me, I've been up forever, so it probably don't make any sense at all. And I'm going to use this image file, blueberry. Oh, here, we'll just try this first, and we'll show you that's an ordinary file. So it says there's no handshake inside. It's a clean file. But I'm going to stuff the Unix file inside it. And now, I'm going to remove the Unix file. Actually, we're going to have a look at it first, and then I'll delete it. It's quite large. So that goes on forever, right? And if we did a word count, you'll see it's 31,000 characters, 8 bits per character. And now we will remove Unix text, and it is no more. And we can see that in a graphical way, that now we have just the new image we created and no text file. Now we're going to have a look at the new image with the image viewer, and it looks just like the blueberry pictures, and there they are. Here's blueberry, there's the image, and you can tell the difference. You got some sharp eyes on you. Now we have a close look at it with a hex editor. I still defy you to see the difference, but I'll show it to you a bit more. Okay, our pixel colors start here, and we got 42, which is 66 in decimal, and 84, 72, 52 is 82. These here represent blue, green, and red to the bitmap image. But to me, I've flattened them out and made sure they were all even. And I've done this with 8 sets of pixel colors. And then I did 8 sets of them with odd encoding. I'm only moving the pixels by 1 number so you can't see it with the naked eye. But I've got even odd encoding, which has created a handshake. The rest of the even odd encoding throughout the rest of this, how many million, 1.3 million pixels, is creating the characters. And this is done with, by taking, we're only using 2 libraries here in the C language. We jam the header into a structure. The pixels go into a structure one at a time. We use a linked list, no matrix, because we're not doing anything with the pixels. We're just ramming them in and out, marshalling them. And I don't care if they're red, green, blue, whatever they are. And yeah, the Matrix was a really stupid movie, so had to avoid that. That's some ugly, ugly code. But if we get up here to, I think it's the encoder, Yeah, right here. This here's actually bitwise manipulation of a character. So the character, let's say it was a capital A, which would be decimal 65, and represented in binary is 0, 1, a whole bunch of zeros and a 1, yeah. And this here would strip the last 1 off. First it checks to see if it's an even or odd number, then rips the least significant bit off and keeps going through a loop checking it over and over again to see and make an even or an odd pixel out of it. And there's no, like I said, no real obvious difference between the two images, but one contains 24,000 bytes of text. Alright, let's see this thing in action. Bitmap, hack, image, pipe the output to less, and alright, the Blueberry picture now has 70,000 bytes of text in it. So I overcome some of the issues with the size. And this here larger image has 450,000. Sending the output of the program to standard out has a major benefit when you're using the pipe on the command line. So we can pipe it to word count, head, or even grep as a filter to search for content inside a text file that's hidden inside a bitmap file structure within a file structure.